In the previous video, we have shown that a reaction typically takes a while to reach the equilibrium. Typically, if you start with only reactants, the reactants will disappear slowly and products will appear as slowly as reactants disappear until you reach or until the reaction reaches an equilibrium situation where concentrations are constant over time. A very graphical way to represent that is like in this graph, when you represent concentration over time. In this case, you are starting with only reactants, that certain amount, and you have zero products at the beginning. This means that the concentration of products will increase and concentration of reactants will decrease until the concentration here is kept constant. That's what we call dynamic equilibrium. Again, it's not that the reaction stops, it just means that the rate at which reactants become products is equal to the rate at which products become reactants. So notice that also the proportions that you end up having of reactants and products is telling you how the value of the equilibrium constant. In this case, because in equilibrium you have more products than reactants, it means that your equilibrium constant will be larger than 1. And notice that because the matter cannot be destroyed, the amount of reactants that disappear has to be equal to the amount of products that appears. In this case, if you have like 10 moles of this and 10 moles of this, you'll end up having, careful here, you have 20. So the amount, and that kind of makes sense, this number of moles of products is equal to, again, more or less, this amount of reactants that have disappeared. Let's see if we can represent that in two graphs. In this case, this exercise asks us to represent a concentration of it over time graph corresponding to this reaction and with this kind of value. It has to be a qualitative graph, but this just says that you'll have more products than reactants because your equilibrium constant is much larger than 1. So if we start with equal amounts of A and B, let me do it in a way that it will. So if you start with A and B, notice that if you have 10 moles of A and 10 moles of B, you'll end up having 30 moles of C. So that means you'll go from 20 to 30. So if this is 10 of each, and again, because this is the equilibrium constant is very small, it'll end up not exactly 0. Reactions are never never completely eliminate reactants, but the amount of products will be, and I'm gonna run out of scale here, because if this is 10 and this is 20, the 30 probably is up here. Sorry for out of scale, right? I even went a little bit too high, but it should represent the amount that you're gonna obtain of products. Okay, and when these two graphs plateau, that's when you call this equilibrium. Okay, in this case, it's asking us for represent the concentration over time for this reaction in a situation where the equilibrium constant is smaller than 1. That is, you'll end up having more reactants than products. So if you start with, let me give you an example. If you have 10 like this and 10 of this, you'll end up having, again, 10. So you started with 20, you'll have only 10. So if you start with A and B of this, well, that's not true. When the reaction is completed, you will still have more reactants. So this will be, oh, careful here. If this is A, this will be B. Why is that? Because notice that for each mole of A that reacts, twice as much of B will react. So maybe it's not quantitative, but this should be twice as much. And C will be as much as A, so we have to make sure that this is C. So there you go, got something like that. Okay, still in equilibrium, you will have more reactants than products because your equilibrium constant is smaller than 1, and make sure that the stoichiometry the stoichiometry tells you the quantities that you'll have in equilibrium. That is, as much as reactants disappear, you will have products appearing, as long as there is a 1-to-1 ratio. So the amount of A that disappears is the amount of C that appears.